help you where I'm at. Please, if I made a change and it's not what you have, please tell me along the way, all right? So if I were to, I like a picture here, so 0 to 8, 4, 3, 2, 6. Okay, so if I draw this really, really spread out, it would look like that. If I were to use left-hand rectangles and 4 of them, then wouldn't my LRAM or left rectangle approximation method be something like the area, I'm going to say the area is equal to or approximately equal to? Approximately equal to. And if they're equal subdivisions, then rather than do 4 bases, could I just factor out a base? Yes, okay, so rather than do 1 base times height, 1 base times height, 1 base times height, 1 base times height, I'm just going to factor out a base and then talk the heights. Now, the heights, if it's left hand, then do I draw my first height at f at 0 or f at 2? 0. So the first height would be f at 0. The second height from 2 to 4, where's the height at? At 2 or at 4? 2. The third height is f at 4. And the last height is f at 6. And the base, I remind you, is the delta x. And so I would get, let's go with, what's the base? Delta x is 2. What's f at 0? 1. What's f at 2? Did I forget one? I forgot one. Sorry, catching up. What's f at 2, did you say? What's f at 4? And f at 6. 37. So my estimate of the area is 120 is what I'm doing? Yes. Can I get a yes on 120? Okay, 120. Tell me, based on the picture, is that an overestimate or an underestimate? Underestimate. How could I get a better estimate? Okay, I could take a limit infinitely many. I could do more rectangles, 8 rectangles, and minimize the area. We'll do that in a second. But let's go to RM. It is an estimate. The area is approximately. The base is still 2. I'm just going to write the delta x in 2. The heights for RM, f at what? F at 2, f at 4, f at 6, and f at 8. Okay, so that might be something like 2 times 5 plus 17 plus 37 plus, what's f at 8? 65. And 2 times, let's see what we got there. 22, 23, 59, 124 maybe? Is that right? 102, 124. I got 124 inside each time, so what, 248? Yes. Okay. Is that an overestimate or an underestimate? Over. So we know the true area lies somewhere between 120 and 248, which is quite a different range. Let's try midpoint. Midpoint is number, I guess. What's the base of each if I do midpoint? Still 2. But now the heights are the midpoint of each subregion. So f at 1, f at, f at, and f at. So 2 times, what do we got there? When I put 1 in, I get 2, 10, 26, and 50. So that's 60 plus 28. So 88 times 2, what do you get there? is 76. Okay, which is the most accurate of the three? Okay, so what's 76? Later on we'll talk about what's called Simpson's rule. Simpson's rule uses a blend of methods. It uses trapezoids and midpoint, a weighted average, and it gets doggone close. But we'll talk about that later. For now, that'll do. Now, the problem is sometimes, especially without a calculator, you don't have such nice pretty princessy kind of numbers. So imagine if you had the square root function from 0 to 16, and you wanted the area under that. But you are not allowed to use a calculator. Well, if you're not allowed to use a calculator, then I don't want to talk about, hey, what's the square root of 8, and the square root of, well, square root of 4 is okay, and the square root of 12. Those are ugly. So equal subdivisions would be bad, because I get values that are hard to work with. Instead, you would choose values that are nice to work with, even if it gives you unequal subdivisions. So what are some nice numbers to work with in the square root function? Well, 1, I could use 1, and 4, and 9, and 16. I would get different regions, and that's okay. Because they're different regions, can I factor out a base now? No. No. All right. So in LRAM, I would say more like the area is approximately the 4 rectangles. So the first, each time you're going to take a delta x times an f of x, and there will be 4 of them. So you could say that you're going to take the sum of a couple different delta x's times f of x's, and they're going to vary each time. So you're going to have a first delta x and a second delta x and a third delta x and a fourth delta x from 1 to 4. Again, we're trying to get you a little more comfortable with summation notation. It'll be a gradual process. Okay, now then, let's go back to expanded form because students feel better with it. The first, if I use LRAM, first of all, what's the delta x for the first? 1, and what's the height of the first? F at, if I'm using LRAM, then I use F at 0. The second region, which I'm going to go here in green, what's the delta x? 3, and F at 1. And the third region is between 4 and 9. What's the delta x? 5, and F at 4. And the last is from 9 to 16. What's the delta x? 7, and F at 9. Yeah? Let's skip the arithmetic. Okay, let's just move on. I assume you can do arithmetic. That's cool. Would you set up RRAM for me, please? The expanded form. Don't worry about the summation notation. You get the same deltas, but your heights are now f at 1, 4, 9, and 16. Yes. Okay. Notice it doesn't say midpoints because that would give you some nasty points to work with, which is not the point of this problem. All right. Moving on then. If I asked you to use a table to estimate what I want you to do, would you give me, let's just do left hand and midpoint. Would you do a left hand and a midpoint to estimate? I'm a big fan of taking one step to communicate your thinking, then plugging in from the table. So I would prefer it not just be a bunch of random numbers without structure. you get 150 for your left? Or you're still working? Okay. So check your work. You should definitely be communicating, hey, these are the places I'm going to find my heights. To me, that green step is the most important part. Not the answer, but the where I came from. Kind of thing. This is next. All right. Do we agree with 150 or did I make an error? I don't hear a lot of uh-huh. You what? We're good? Okay, cool. How about midpoint, please? Would you do midpoint? Okay. Go back here. Did you get 160 or still working? 160. Cool. Question for you. When will left-hand rectangles underestimate? When the curve is, okay, it's not increasing or decreasing. So left hand will underestimate when it's not increasing or decreasing. Concavity has nothing to do with it. When it's increasing, do you agree? If it's increasing, the left will be less than the right, and you'll get an underestimate. So left hand will underestimate an increasing curve, and right hand will overestimate an increasing curve. And on a decreasing curve, what will happen? Left will overestimate, and the concavity is an issue for trapezoids, but we'll talk more about that later. All right, next idea. Express an area under a curve starting at a left endpoint using right hand, blah, 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 and expanded or summation notation. So let's go here. This is where it might start to get a little uncomfortable. Same deal, x squared plus 1 from 0 to 8. And this time, instead of dividing it into 4 rectangles, I'm dividing it into any number n rectangles. All right, so let's start here. What's the delta x? If I take a region of 8y and divide it into n chunks, then the width of each is 8 over n. All right, cool. Now, if I then mark 8 over n, and I know you want to write 16 over n, but don't. Instead, write 2 8 over n's, and 3 8 over n's, dot, 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 until you get to how many 8 over n's will there be? N 8 over n's. What do you call n 8 over n's? 8, until it ends at 8. All right, each width is an 8 over n across. All right, so here we go. The area then, each time will be first base times the first height, and a second base times the second height, and so on. But isn't the base common to all? Every base is how well? 8 over n. All right? Now, let's talk the heights. We're using right-hand rectangles. So the first height, will it be at 0 or 8 over n? If I'm using the right side, I use 8 over n. So the first height is f at 8 over n. The second height is between 8 over n and 2 8 over n's, and we would draw it the right side, so 2 8 over n's. The third height is f at 3 8 over n's, dot, 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 ending at f at 8 or n 8 over n's, whichever you like, they are equivalent. The last 8 over n. You follow? Okay. Now then, that's an equation to estimate the area under x squared plus 1. I guess I could put in the function. We could do that, but we'll leave it go. But it says, I want to do this also with summation notation. This is called expanded form or expanded notation. And although it's usually a little clearer to students, it's also a heck of a lot more writing. Instead, let's go summation notation. So if we were to write this as a sum, we could say every time there's just an 8 over n floating there, but in the brackets, there is a sum of many functions. Now then, you typically, when you write summation notation, you include, hey, what's the counter here? Let's call it, we can't call it n because n stands for something else, but wouldn't you agree what's counting is how many 8 over n's? 1, 2, 3, dot, 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 dot. It's going up by 1 each time till it ends at n, yeah? Now we can't use n, so what do you want to call the counter variable? X is no good. Let's call it I. Okay, I and k are the most common indices for summation notation. So this is going to be replaced by an I. When you identify the thing that's counting each time, that's the counter in the summation. And what's always there the same is how many 8 over n's. Now then, after you've identified the variable, this is not n to infinity. I hope you didn't write that because that's just nonsense. The counter is I, and it starts at. Well, in this expanded form, what did I start at? Started at 1. And what did it end at? N. The last, what is that? Now you try. Handing back 2 stacks of homework, homework 5, 6, and 7. So just take yours out and pass the 6 stacks. So you should have one in each stack. Okay. Let's see how we did here. I guess I don't need the graph here, but did the graph help you at all? Yeah, I'm visual, so I'm going to draw it. Right 2 or right 1. Oh, geez. Didn't you say, hey, I got a problem? You guys are not very critical thinkers. Did anybody occur to you, hey, what the heck?
Yeah.
You got a little domain issue? You just, whatever, I'm just gonna mindlessly plow ahead. He must know. No, I don't know. Hello. Jeez, people, this class is gonna be a struggle. You guys are way too passive. Besides the brown fellas, I don't even know if both of you talk. Are both of you talking when you shout stuff out, or just one? Whatever. Those are the only guys that are actually engaged, so you guys better wake up, because this is not going to go if you don't. I hate to tell you, it probably won't matter too much, but I'm going to change that to x plus 1, so I actually have no domain problem. Then, 0 to 2, so it's from here to here. Okay, cool. So the delta x, did you get that it was 2 over n? Okay, cool. The area then is that base factored out and f at. Now, if I divide this, the first subdivision, or 1 delta x over is 2 over. 2 delta x's is 2 over n's, 3 2 over n's, and so on. So rather than simplify, you don't want to say 4 over n and 6 over n. You want it to be an obvious counter in there, so it's easy to write the summation. So I prefer you have something like 2 over n, f of 2 over n's, f at 3 2 over n's, through f at n 2 over n's. Did your expanded form go something like that?
Yeah.
Okay. Second, did you have something like 2 over n f at what? I 2 over n's from an I starting I of 1 to an ending I of n. All right, cool. Question for you. Start laying this groundwork. What if it were left? The base would be the same. Do you agree? Okay. Where's the first height at? F at 0. Then the next height is f at 1 2 over n or 2 over n. Then f at 2 2 over n's. Think critically. Where's the last height? F at 1 before n minus 1 2 over n's. So if you were to write that in summation notation, that's going to be probably, that's what we do. F of, inside is f at what? It's still counting how many 2 over n's. That's not changed. What's changed is the indices. What's the start? 0 and n. Okay. Now, all right. Let's go on to the next part. Okay, so let's go backwards. I'm giving you 7. Okay, backwards. I'm giving you summation notation. I want you to tell me. Oh, that's why I should have used the functions instead. You go back and do one extra step on for this. What if I had done here one better and actually put the function in? Given that it was x squared plus 1, and that's what I was putting in, what would it look like in there? The function is blank squared plus 1, and what's going in? I times 8 over n. And from that, you get a little more. The function goes in, all right? So with that said then, with these, this is surely the delta x, and this is the function. So hopefully you should be able to tell me what's the function they're finding the area under, and what's the region. So what do you reckon the function is? 2 minus x cubed. And what's the interval? square root of 3 because the width of the region is 3. Okay, cool. You try. Are you ready? What's the function? 2x cubed plus x, I agree, x, not 5x. X, and what's the interval? 5. Okay. Okay, now here's the problem. We're actually making a gross assumption, and that is that the width of the interval is 5, and we must have started at 0. Why? How do you know it starts at 0? Why didn't it start at 1 and go to 6? Or 2 and go to 7? You don't know that it started at 0 and went to 5. You were making a large assumption and hoping that it was a pretty princess case, which I'm fine with because you can't really tell anyway. So that's fine, but let's look at one. Well, what happens when you don't start at 0? Things start to get a little hairy. All right, so here we go. This time we have x squared plus 1. And we're going from 1 to 8. So that region there okay. All right. Let's start with the delta x. What's the delta x? 7 over n. The width now is 7 wide, and we're dividing it into n chunks, so each chunk is 7 over n wide. We're using equal subdivisions. Cool. All right. Now, the hard part. So the area is the base of 7 over n times the heights at who knows where. We're using right-hand rectangles. And so when we go starting at 1 and travel a 7 over n over, what x does that put me at? x1 is 1 plus 7 over. What's x2? 1 plus 2, 7 over n. And then x3, 1 plus 3, 7 over n's, dot, 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 through the last. The nth x, there should be, it said n subdivisions, so we should have an nth x. X of n is 1 plus n 7 over n's, which is equivalent to 8. 8 plus 7 is 8. All right, then. So my first height is the function at what x value? F of 1 plus 7 over n. And the next is f at 1 plus 2 7 over n's, terminating with f at 1 plus n 7 over n's, or 8. They're both true. We? Okay, let's write that in summation notation. 7 over n is just hanging outside. Inside is f at different x's. And so what is the pattern? F at what? What's always there? What's counting? That's what I asked myself. What's always there and where's the counting? Here's the counting. And everything else is always there, so it needs to be here also. So F at 1 plus I 7 over n's. What's the starting I? 1, and the ending I? N. But if it was left-hand rectangles, what's the starting I? 0, and the end is n minus 1, because everything is in the left side, it would start at 0 and end at 140. Yeah? Okay, cool. If I went one better and put in the function, let's talk about what it might look like. The function is blank squared plus 1. So if I put in blank squared plus 1, and inside the blank I put in what I'm supposed to put in, then what's in? I don't think I understood what I just said. If the function says put something into the functions, square it and add 1, then what do I put in? All right, cool. Is this a good one to put this idea in? Okay, I'll get it in a second. Sorry, I just want to make sure I hit all the ideas, but I don't want to throw too much at you at once. Would you change this to x plus 1? And then try one on your own, please. Pretty good. Nothing missed so much that I need to go over it. So if you miss something, go with me individually or go over it. And you can't find a mistake on it. I was happy with having it. So. Okay. Okay, do you have something like the summation from 1 to n of 4 over n times the square root of 1 plus I 4 over n or I 4 over n plus 1? Yes? Okay, cool. So here's the problem that sometimes students have. The fact that there's a sum in there kind of tells me, oh, it's starting at 1 and it's 4y. But what if they had simplified it and it looked like the square root of 2 plus I 4 over n? What would that kind of indicate? What would it seem like the function is then? Maybe 2 plus x. And what's the starting value? Maybe 0 to 4. how can it be two different things? Well, this region would look just like this. Okay, imagine if I graph this region. 2 plus x would be left 2, starting from 0 to 4. Wouldn't this region from 0 to 4 with 2 plus x be exactly like that region? And so they're the same, it's just a different way of looking at it, and there are multiple answers. So on the AP test, obviously they wouldn't put two different answers, or on a multiple choice test, they would put two possible answers that are the same. You would just have to find one that's working. So try this and see what you think. Oh, actually, let's do one together. My bad, sorry. What's one possible function here? If we assume it's not starting at 0, it's starting at 2, then if we assume it's starting at 2, then how far do we go to the other end? 3 more, so 5. If I do that, then that 2 is not part of the function, it's part of the starting x. So what is the function? X cubed, okay? Now, let's say that I consider that part of the function. And it's 2 plus x cubed is always what you get. Then what would the interval be? 0 to 3. Yeah. Could you even go 1 plus x cubed and 1 to 4? Yeah. Okay. So, 2 possible answers, at least, that are obvious. Do one, I don't care which, and if you're not sure if yours works, let me know, and I'll be happy to give it a little look. Okay, what's one possible, say you started at 4, then what's the end point? If you did that, then the 4 is not part of the function, it's part of the x, and so what's your function? Natural log of x. Say you said that natural log, that 4 is part of the function, then what's the function? In which case, what's the starting and ending value?
0 to 5.
Okay. Those are the most logical, but again, there are infinite many possibilities. Okay. Apparently, that's all I got rid of got through last year's, but we're just cruising. Is this the next thing in your notes? Yes? Super. Okay. Now, this is where it gets fun. Okay. So, first of all, there's all these great summation formulas. Some of these make a ton of sense, and some of these not so much. This guy, what does this mean? How do you decode that? What am I adding, and how many times?
Summation of C's.
I'm adding a bunch of C's to itself so n times. Well, isn't there a shortcut for that? If I add 2 to itself 3 times, isn't that the same as 2 3 times, or 2 times 3, or 6? So if I add C to itself n times, isn't that just what multiplication is? C times n, or n, C n times, yeah?
Yes.
This one is my favorite. This is where we have a good story. Would you agree that this is 1 plus 2 plus ... through n? That's what that means, yeah? That's what the summation means. You with me?
Yes.
Okay, now I give you what this formula is, but this is a cool, I shouldn't have given you this. Pretend you don't see that, okay? Ignore it. So have you heard the story behind this about the little 5-year-old?
Yes.
You have? You have? This is a cool story. Okay, so check this out. This is about 300 years ago, 400 years ago, and there's this group of German kids, and they're a bit of a mixed bag. It's anywhere from 5-year-olds to 9-year-olds because they're a ability group, okay? So one day this German teacher says, man, I'm just not feeling it today. So he puts this problem on the board, and he says, you know what, kids, I want you to do this. Add 1 plus 2 plus 3, and I want you to go all the way to 100. and get that sum and come up to my desk when you're done, okay? And so he figures, okay, well, that'll take forever. So he sits down at his desk and he starts reading his German paper, and he figures, I got forever. Well, not 10 seconds later, some little, the smallest, youngest kid in the class, this little snot-nosed kid comes up with his slate. They did their practice problems on a slate on a chalkboard, yeah? He had no work and just, that's my answer. Takes it, get out of here, go do the problem. I want to read my paper. He says, no, I'm done. That's the right answer. And he goes back and sits down. Well, the teacher is fury, does the stupid problem, he adds it all up, and sure enough, this kid did the problem in 5 seconds. And the answer is 5,050. How did he do it? Yeah, so depending on how you group, you could group this way. He did, basically, in essence, he did the old rainbow. If you add 101, that's 100, you could do 199. Do you agree that's 101? Every sum is 101. And then the only question is, how many sums? Well, if there are 100 numbers and I paired them up, how many sums? 50. So he took 50 times 101 and did that mentally. You might think, oh, sure, 5 though. Now this is the greatest human being of mathematics of all time. That's Gauss. And so he did that, like, that's the story goes. I don't even know if this is, it's sort of a legend, I don't know. But this guy is my hero. Gauss is the greatest mathematician of all time, even greater than Newton and Leibniz. This guy is so amazing. He had like a doctorate at 14. Wait, you guys way behind. You're not smart at all compared to him. He got so bored coming up with new theorems that eventually he just started sending them off to his friends to say, you take credit for that. Well, I don't know. By the time he was 19, he already had a whole book of theorems after. This guy is like, I mean, it makes Rory Devon look like I mean, the guy is brutal. Oh, so cool. Okay, so at any rate, that's the idea behind this formula. If you take that idea, didn't you take the first and the last and then multiply it by how many pairs? Yeah? So what's the first? 1. In this case, what's the first? 1 and the last. And then how many pairs? If there are n numbers, then how many pairs of numbers? N over 2. And so that's where the formula comes from, is by pairing them up and multiplying by how many pairs. Now, these are starting to get more complicated, but I will throw a little calculus idea. Proving these is a really fun and crazy, wicked exercise. And if you get into how they change, you'll actually see some calculus in there. The change rate in this is a square. The change rate in this is a cube. The change rate in this is a 4th degree. There's some cool calculus in there, and it's fun to do on a Friday night if you have no date. Okay, so let's look at this one and talk about how these are used, and I'll show you where those come in. For now, they're just some formulas sitting up there. I'll show you how you use them. We have 4 minutes. We might get through this one. Here we go. When I draw this, I have zero care of what the graph actually looks like. I'm not meant for this to be exact. It's just meant for me to get a clue for what the interval would look like. The graph doesn't have to be accurate, all right? If I break this up into n chunks, then what's the delta x? 4 over n. And the area then is 4 over n and f at what? What's my first x if I'm using right hand? X1 is this a starting value plus delta n case, or is it just straight up starting at 0, so just about the delta n?
Delta n.
So it's f at 1 4 over n plus f at 2 4 over n's, terminating at f of n 4 over n's again, because we're using right-hand rectangles. That's why that happens. Very cool. And summation notation, then, that's the sum of many 4 over n's times f at, and what would you express that stuff as? I 4 over n's with I starting at 1 and going to n. Now, here's where we're going to go a little more detail. If in this case the function is x cubed plus 2x, then doesn't that mean 2 input places, blank cubed plus 2 blank, and in those blanks we put I 4 over n. So are you with me?
Yes.
Okay. Now the problem then is that's, so far we just kind of stopped there. So, all right, whatever, there you go. There, you can do more. You can do more. You can dump the summation, for example. So check this out. First thing, now we're going to do some algebra with n. We're going to isolate I cubed and I. And I'm not sure why I started with such a terrible function. I should have started off with one easy one. That's terrible. Oh well. All right, so here's my thing. I can, first of all, break this up into 2 summations. One for the 4 over n times the cube, and one for 4 over n times the 2e kind of thing. Are you with me?
Yes.
And I did not give myself enough room. Wish I would have written small. All right. Now, in terms of this guy, does this counter apply to the n stuff or just the I stuff? That question didn't go anywhere. So let me say this. Every time I put in an I value, isn't this stuff just going to be there? 4 over n and 4 over n cubed, it's just going to be there every time, right? And I'm really just talking about what about the I stuff. So couldn't I don't have time to finish this. All right, so here's the deal. We're going to do this over 2 days. So I would look through the last page, and any problem that you can tackle tonight, you probably would want to do a little of that. The last page is practice problems. The first 3 pages are noting problems, so we'll finish the notes tomorrow. Just do a little of the last page, and we'll finish tomorrow. Okay? Have a great day. So this homework will be due Thursday. So I guess you could read it that as no homework tonight and a lot of homework tomorrow. Why don't you keep last night's also on the table night grading. Turn that in tomorrow. So review. Yes, lazy reasons rejoice. Review 9 is due tomorrow. 10 is due Thursday. Okay. Have a good day.